The Oort cloud is so incomprehensibly large that the entire planetary solar system, every planet, every moon, every asteroid belt, sits at the very center of it like a grain of sand at the bottom of an ocean. Almost nobody talks about this. Hit that like button, subscribe if you haven't already, and drop a comment telling me where you're watching from and what you're doing right now. I genuinely love seeing who's out there. Now let's get into it. There is a place at the edge of our solar system so vast, so cold, and so far outside anything the human mind can comfortably process that even astronomers who spend their careers studying it sometimes stop mid-sentence when they try to explain it. No dramatic images exist of this place. No spacecraft has ever visited it. No telescope has ever photographed a single one of its objects where it actually sits. And yet it is real. It surrounds us in every direction, and it stretches so far that the word distance stops working somewhere along the way. This is the Oort cloud. The fact that most people have heard the name but carry no real conception of what it is, how large it actually is, or what it means for our position in the universe, that might be one of the most consequential gaps in popular science education. Because once the Oort cloud's true scale lands on you, the solar system you thought you knew will never look quite the same again. Start with what you probably already know, just to build the foundation before things get strange. The Sun sits at the center. 8 planets orbit it in a nearly flat disk. Mercury holds the closest position, at about 36 million miles from the Sun on average. Earth orbits at 93 million miles, and astronomers call that distance 1 AU, 1 astronomical unit, which becomes the yardstick for everything that follows. Mars sits at about 1.5 AU, Jupiter at 5.2 AU, Saturn at 9.5 AU, Uranus at 19 AU. Neptune, the farthest full planet, orbits at about 30 AU. Pluto, the famous dwarf planet stripped of its planetary status in 2006, traces an average orbit of about 39 AU. Beyond Neptune lies the Kuiper Belt, a region of icy bodies and dwarf planets stretching from about 30 AU to about 50 AU. Pluto lives there, along with Eris, Makemake, Haumea, and thousands of smaller objects. The Kuiper Belt is itself enormous by human standards, a structure 20 AU thick, filled with the frozen leftovers of the early solar system, catalogued by scientists for decades, without anyone reaching the end of the list. And yet, measured against the Oort cloud, the entire Kuiper Belt amounts to essentially nothing. The front porch, the driveway, the strip of sidewalk between your front door and the street, when the street is in another state. The Oort cloud doesn't begin until roughly 2000 AU from the Sun. Some estimates place the inner edge closer to 5000 AU. The outer edge sits somewhere between 100,000 and 200,000 AU away. The numbers alone don't carry the weight. We need to think about these distances in terms that actually communicate the reality. At 1 AU, light takes about 8 minutes to travel from the Sun to Earth. The Sun you see in the sky right now left its source 8 minutes ago. Neptune at 30 AU is about 4 hours away at the speed of light. Pluto is around 5.5 hours. The outer edge of the Kuiper Belt, at 50 AU, sits roughly 7 light hours from the Sun. Now the Oort cloud. Its inner edge, at 2000 AU, is about 11.5 light days from the Sun, not hours, days. And the outer edge, at 100,000 AU, is roughly 1 year and 8 months away at the speed of light. Close to 2 years. The outer boundary of our solar system is so remote that light itself, the fastest thing the universe permits, takes nearly 2 years to cross it from the center. Proxima Centauri, the nearest star to our Sun, sits at 4.24 light-years away. The outer Oort cloud reaches between 1/4 and 1/2 of the distance to that star. Our solar system doesn't end where the planets end. It doesn't end at Pluto. It doesn't stop at the Kuiper Belt. The Sun's gravitational sphere of influence pushes outward until it's practically in contact with another stellar system. That is what the Oort cloud actually is, the full, true extent of our solar system, and almost none of it can be seen. Before going further into the scale, there's a story worth telling about how we know this thing exists at all, because the discovery didn't come from a telescope pointing at it. It came from comets. Comets have been watched, feared, worshipped, and catalogued by human beings for thousands of years. Ancient civilizations read them as omens. Medieval Europeans held them responsible for the deaths of kings. Chinese astronomers tracked them with meticulous precision. For most of human history, comets were mysterious arrivals from the darkness beyond the known sky, and nobody could say where they originated. By the 20th century, astronomers had established that comets were balls of ice and rock, moving along highly elongated orbits around the Sun. Heat from the Sun vaporized material off the surface as a comet approached, and that vapor formed the glowing tail visible from Earth. Origin, though, remained an open question. Two broad categories of comets exist. Short-period comets complete their orbits in under 200 years. Halley's Comet returns approximately every 75 years and represents this category well. Astronomers trace these comets to the Kuiper belt, their orbits shaped and shortened by repeated gravitational interactions with the outer planets over millions of years. Long-period comets behave entirely differently, orbital periods of more than 200 years, often millions of years. They stream into the inner solar system, blaze past the Sun, and then disappear back into the dark, not returning on any timescale that connects to human history. Some complete a single pass and never return. Their trajectories are hyperbolic, meaning they swing through and then fly off into interstellar space permanently. The puzzle with long-period comets was their arrival direction. Short-period comets, originating in the flat Kuiper belt, mostly approach from near the plane of the solar system. That makes geometric sense. Long-period comets come from above the plane, below it, from the sides, from every conceivable direction. Their source, whatever it was, couldn't be a flat disk. A spherical source was the only geometry that fit the data. Jan Hendrik Oort, a Dutch astronomer, analyzed the orbital patterns of known long-period comets and published his conclusions in 1950. The comets had to be coming from an enormous, roughly spherical shell of icy bodies at an extreme distance from the Sun, held weakly by the Sun's gravity, and perturbed occasionally by forces that sent individual objects falling inward on new trajectories. He never saw a single object in this reservoir. He deduced it from the comets it was delivering, and the deduction turned out to be correct. Oort is worth a brief moment of appreciation here. The same astronomer who calculated the rotation of the Milky Way galaxy published the Comet Cloud paper in 1950 and continued working in astronomy into his 80s, eventually living to 92. His name now applies to a structure nearly 2 light-years across, containing trillions of objects. That's not a bad legacy. An Estonian astronomer named Ernst Öpik had proposed a similar reservoir in 1932, nearly 2 decades before Oort's paper, which is why some astronomers use the name Öpik-Oort cloud. Oort's version of the argument provided the observational analysis and mathematical framework that persuaded the broader scientific community, so his name took hold in common usage. Öpik gets the historical footnote. Oort got the cloud. The theory earned acceptance not from any direct observation, but from the absence of any other coherent explanation. Long-period comets had to come from somewhere. They arrived from all directions. The math pointed to a vast, distant, spherical reservoir. Every serious astronomer today accepts the Oort cloud's existence, and not one of them has ever seen it directly. No direct image of the Oort cloud exists. Not one object has ever been photographed sitting undisturbed in its natural position out there. Everything known about the cloud comes from inference, from mathematical modeling, and from the behavior of the comets it sends our way. The whole structure is, in the strictest sense, theoretical, and also, given the evidence, essentially certain. We are surrounded by a trillion-object structure that extends halfway to the nearest star, and the only way we know it's there is that it periodically throws snowballs at us. Scale analogies work better than raw numbers, so try this one. Shrink the entire solar system, Sun at the center, Neptune's orbit at the edge, down to the size of a standard American quarter coin, 24 millimeters across. Neptune's orbit at the rim of the coin. Every planet, every moon, every place any human spacecraft has ever reached, contained within a circle smaller than your thumbnail. Now find the Oort cloud on that scale. The inner edge, at roughly 2,000 to 5,000 AU, sits between 5 and 12 feet away from that coin. The outer edge, at 100,000 AU, is about 500 feet away. More than 1.5 football fields, and at the far end of those football fields is the edge of our solar system. Between the coin and the outer edge, empty space, frozen objects spaced incomprehensibly far apart, and the gradual fading of the Sun's gravitational authority. Try the thumb measurement instead. If the Earth-Sun distance equals 1 inch, the length of the tip segment of your thumb, the outer Oort cloud sits about 1.6 miles away. Proxima Centauri, the nearest star, is at about 6.5 miles on this scale. The entire solar system as most people picture it, planets, asteroid belt, Kuiper belt, fits within 2 inches of your thumb. The actual gravitational reach of our Sun stretches 2 miles. Another 4.5 miles of empty space beyond that leads to the next star. Those are the real proportions of our neighborhood. Space, properly understood, is less like the star-filled canvas of science fiction, and more like an almost total void, scattered with tiny, isolated points of warmth. The objects drifting in the Oort cloud aren't random debris, they're relics. Preserved leftovers from the solar system's formation 4.6 billion years ago, when the Sun was surrounded by a spinning disk of gas and dust from which the planets coalesced. Not everything in that disk became a planet. Jupiter and Saturn, as they grew, worked as gravitational wrecking balls, flinging enormous quantities of smaller bodies outward on new trajectories. Material that didn't fall into the Sun, didn't merge into a planet, didn't get swept up as a moon. Much of it ended up ejected far out into the outer solar system on highly elongated orbits. The galactic environment then took over. The combined gravitational pull of the Milky Way galaxy's hundreds of billions of stars doesn't just exist at the galactic center, it permeates the space around our solar system, creating tidal forces that operate on weakly bound outer objects. Over hundreds of millions of years, these galactic tides pulled at the far ends of those elongated orbits and gradually lifted the closest approach distances, circularizing them into the roughly spherical distribution known today as the Oort cloud. Some of what's out there may not even have originated in our solar system. When the Sun was young, it was probably part of a birth cluster, a group of stars that formed from the same molecular cloud and then gradually dispersed over time. During the period when those neighboring stars were still relatively close, gravitational interaction meant material could transfer between young stellar systems. Icy bodies that formed around neighboring young suns may have been captured by the growing Sun's gravity and incorporated into its outer cloud. The Oort cloud may contain material from multiple stellar birthplaces. The objects themselves are composed primarily of water ice, ammonia ice, and methane ice. These were the volatile compounds that couldn't condense near the warm young Sun. They needed the cold outer regions beyond what astronomers call the frost line. When a comet blazes through the inner solar system, the tail of vaporized ice visible from Earth is a direct look at the original chemistry of the early solar system, finally melting after 4.6 billion years in cold storage. The temperature out there is nearly impossible to relate to anything in ordinary experience. Between -220 and -270 degrees Celsius. Absolute zero, the theoretical floor where all molecular motion stops, is -273.15 degrees Celsius. Objects in the Oort cloud sit within a few degrees of that floor. They've been in something close to suspended animation since before Earth existed, receiving almost no energy from the Sun, whose warmth falls off as the square of distance and has essentially no effect at 100,000 AU. At those distances, the Sun doesn't look like our Sun, it's a star. The brightest star in the sky, by a significant margin, roughly as bright as Venus, appears from Earth on a clear night, but a star nonetheless. Standing on the surface of an Oort cloud object, you'd look out at a sky full of stars, one conspicuously brighter than the others, and that bright star would be the center of our solar system. The Earth would be completely invisible, an unresolvable dot orbiting an unresolvable dot, so far away that its light takes nearly 2 years just to arrive. Everything that has ever happened in human history, every civilization, every war, every discovery, every person who ever lived, all of it is taking place on an object that cannot be detected from where you're standing, circling a star that looks like a slightly above average point of light, in a galaxy you're already a faint piece of. That's the Oort cloud's perspective, and it doesn't care at all. The population question comes up quickly when people first grasp the scale, and the honest answer is that we don't know precisely, because no one has ever directly observed the cloud. Estimates come from 2 sources: the measured rate at which long-period comets arrive in the inner solar system each year, and mathematical models of how the early solar system dispersed material during the planet formation era. Current best estimates suggest the Oort cloud contains roughly 2 trillion objects larger than about a kilometer across. The total mass adds up to somewhere around 5 times the mass of Earth. Though the uncertainty range is wide, some models run from 1 to 100 Earth masses. The key point is the sheer number: 2 trillion individual objects, each one a frozen world of sorts, each one preserved since before complex life existed on Earth. Even with 2 trillion objects in it, the Oort cloud is nearly empty by any relatable standard. The space it occupies is so enormous that the average gap between neighboring objects is hundreds of millions of miles. Traveling through the Oort cloud at spacecraft speeds, you'd pass through for centuries without coming within visual range of a single object. The cloud is dense in astronomical terms and operationally indistinguishable from void in any experiential sense. Describing it as full of objects is like describing a cubic mile of atmosphere as full of oxygen molecules. Both claims are true, and both fail to capture what it would feel like to be there. The mechanics of how a drifting Oort cloud object becomes a comet visible from Earth involve forces operating on scales that make the solar system feel small. An Oort cloud object's grip on the Sun is already weak. The Sun's gravity falls off with the square of distance, and at 50,000 AU, that grip is so tenuous that an outside nudge can change an object's orbital trajectory entirely. Several sources provide these nudges. Galactic tides come first. The Milky Way's mass, hundreds of billions of stars, plus dark matter, gas, and dust, generates a gravitational field that extends through the space around our solar system. The differential pull of this field across the Oort cloud's volume, with one side of the cloud slightly closer to the galactic center than the other, creates genuine tidal forces. These tides work slowly but without pause, gradually bending and reshaping the orbits of outer cloud objects over millions of years, occasionally steering one of them onto a path that curves inward toward the Sun. Passing stars provide the second type of disturbance. Our solar system orbits the galactic center at roughly 514,000 miles per hour, and so do all the other stars in the Milky Way, each on its own trajectory. Occasionally another star passes within a few light-years of our system, and even at that distance, its gravitational pull is enough to disturb the weakly bound outer Oort cloud objects, sending some of them on new paths. A red dwarf called Schultz's star passed within about 0.82 light-years of our Sun, approximately 70,000 years ago, about 52,000 AU, and may have dislodged objects that are still in transit, still falling inward, and won't arrive in the inner solar system for tens of thousands of years. Giant molecular clouds provide a third type of disturbance. These massive cold nebulae scatter through the galaxy, and our solar system passes through or near them occasionally during its galactic orbit. Their mass can reshape the Oort cloud in ways similar to a stellar encounter, but spread over longer periods. The result of all these forces is a cloud that, despite appearing still over any human timescale, operates as a dynamic system over geological time. Objects are constantly being slowly perturbed onto new orbits. A fraction of those objects, over millions of years, gradually find their closest solar approach migrating inward until gravity pulls them toward the inner system in earnest. What looks like a frozen, static reservoir is actually an enormous slow-motion delivery mechanism, constantly processing perturbations and occasionally sending one of its contents on a fall toward the Sun. The journey from the Oort cloud to the inner solar system takes anywhere from hundreds of thousands to millions of years. A comet set in motion by a stellar encounter 100,000 years ago is still traveling, still falling, still millions of miles from the point where it will start to vaporize and glow. The comet that blazes across the sky and makes the news for a few weeks might have been in transit since before Homo sapiens appeared on Earth. Specific comets make this abstract idea concrete in a way that nothing else does. Comet Hyakutake was discovered by Japanese amateur astronomer Yuji Hyakutake in January 1996 and passed Earth in March of that year at a distance of about 9.3 million miles, one of the closest cometary approaches on record. Its tail stretched dramatically across the night sky, bright enough for anyone in a dark location to see easily. Observers who were there describe it as one of the most memorable things they've ever seen overhead. Hyakutake came from the Oort cloud. Its estimated orbital period is roughly 70,000 years. The last time this comet passed through the inner solar system, anatomically modern humans were completing their migration out of Africa. Neanderthals still inhabited Europe. The concept of a city didn't exist. Writing was tens of thousands of years in the future. The comet made that previous pass, swung back out into the dark, and has been traveling through the outer solar system ever since. Through the rise of agriculture, the construction of every ancient monument, every war, every civilization, every scientific revolution, the entire span of recorded human history, and then returned in 1996 to be photographed by digital cameras and tracked by modern telescopes, before disappearing again for another 70,000 years. Comet Hale-Bopp is the other standard-bearer for this kind of thinking. Discovered independently by Alan Hale and Thomas Bopp in July 1995, it put on one of the most spectacular naked-eye displays of the 20th century in the spring of 1997. Its nucleus measured around 60 kilometers across, vastly larger than typical comets, which explains why it was so bright. Hale-Bopp remained visible to the naked eye for 18 months, a record. Even people in light-polluted cities could see it. Its orbital period, revised after the 1997 visit based on updated trajectory calculations, came out to approximately 2,520 years. That places the previous visit around 500 BCE, the Athenian Golden Age. Confucius had recently died. The Roman Republic was in its early decades. Hale-Bopp burned through the inner solar system, left no written record that has survived to our knowledge, and then vanished for 25 centuries, during which the Roman Empire rose and fell, the Middle Ages began and ended, the Renaissance happened, the Industrial Revolution happened, and humanity developed the capability to put machines into orbit. When it came back in 1997, the civilization looking up at it was so different from the one that last saw it that the comparison strains description, and 2,520 years is short by Oort cloud standards. Some long-period comets carry orbital periods measured in millions of years. A few complete exactly one trip through the inner solar system and then leave permanently on hyperbolic trajectories, never to return. Comet C/2012 S1 Ison is the case study in that last scenario. Discovered in 2012, it generated enormous excitement because early calculations suggested it might become visible in daylight. Some projections spoke cautiously of a potential comet of the century, an Oort cloud object making its first ever pass through the inner solar system after 4.6 billion years in cold storage, possibly arriving as a spectacular show. The problem was that a first visit from the outer solar system means an untested nucleus. Objects that have made previous inner solar system passes develop a hardened, heat-resistant outer crust from earlier perihelion exposures. A pristine Oort cloud object is still all volatile, unprotected surface. Ison swung within about 1.2 million kilometers of the solar surface in November 2013. The heat and tidal forces were more than it could survive. A nucleus preserved intact for 4.6 billion years disintegrated in hours. The comet of the century died in the attempt. The collective disappointment among amateur astronomers who had been watching Ison for over a year was real and oddly moving. People grieving a piece of ice that had no awareness of their attention, an object that had drifted frozen since before Earth existed, and then simply failed to survive its first and only moment in the light. The structure of the Oort cloud itself divides into two regions that behave somewhat differently. The inner region, sometimes called the Hills Cloud after astronomer Jack Hills, who proposed it in 1981, extends from roughly 2,000 AU to about 20,000 AU. It's more torus-shaped than spherical, flatter, and considerably denser than the outer cloud. The Sun's gravity is stronger at these distances, making the inner cloud more stable against external perturbations. The outer Oort cloud, from about 20,000 to 100,000 plus AU, is the nearly spherical shell that Oort originally described. Its objects are so loosely bound that galactic tides, passing stars, and giant molecular clouds can dislodge them relatively easily. Most observed long-period comets are thought to originate here, because here is where perturbations most readily redirect objects toward the inner solar system. The Hills cloud acts as a slow reservoir feeding the outer cloud. As the outer cloud loses objects over time, some consumed by the inner solar system, some ejected to interstellar space, the inner Hills cloud gradually replenishes it through diffusion, spreading objects outward over millions of years. The system maintains itself on geological timescales, a slow cycling of frozen material from the deep inner reservoir outward to the exposed outer shell, and from there sometimes inward to the Sun. What would it actually feel like to stand in the outer Oort cloud? Not on an object, just floating in space at 100,000 AU from the Sun. The darkness would be absolute except for stars. No day exists there. The Sun provides no perceptible illumination, no warmth, nothing that changes the environment in any cyclic way. The temperature around you would hover between -220 and -270 degrees Celsius. One star in the sky would be conspicuously brighter than all the others. Our Sun, appearing roughly as bright as Venus does from Earth. Everything else you can see would be stars at their own enormous distances, the galaxy arcing across the field of view, no horizon, no up, no down, nothing to fix your spatial orientation. Around you, scattered through billions of cubic AU, the Oort cloud objects drift. You wouldn't see them. Even in the heart of the cloud, the average spacing between objects is so enormous that the nearest one to your position might be millions of miles away, far too distant to detect with unaided eyes. The cloud would be invisible to you from inside it. You'd see only stars, only the dark between them, only the bright point of the Sun and the unresolvable point of Earth somewhere near it. You'd be at the edge of our solar system. You'd also be almost halfway to the next one. And in every direction, in every register available to you, it would feel like you were in the middle of nowhere. Voyager 1 gives us the most concrete available demonstration of how far the Oort cloud actually sits. Launched September 5, 1977, nearly 50 years ago, Voyager 1 flew past Jupiter and Saturn before continuing outward. It crossed into interstellar space, past the heliopause where the Sun's solar wind gives way to the interstellar medium, sometime around 2012. As of 2024, Voyager 1 sits approximately 163 AU from the Sun, farther from Earth than any other human-made object in history. The signal it sends home travels at the speed of light and takes about 22 hours to arrive. At Voyager 1's current speed of roughly 38,000 miles per hour, reaching the inner edge of the Oort cloud would take approximately 300 years, not crossing it, arriving at its beginning. And crossing the entire cloud from inner edge to outer edge would require roughly 30,000 more years of continuous travel. 30,000 years. That's the span back to the last glacial maximum, when ice sheets covered much of North America and Europe, when humans were still hunter-gatherers, thousands of years away from the invention of agriculture. That's the time Voyager 1, our fastest spacecraft, would need to cross the cloud that surrounds our solar system. No mission planning horizon, no institutional framework, no civilization as currently organized would survive long enough to see that mission through. The Oort cloud will almost certainly remain directly unexplored for the foreseeable human future. Carl Sagan's famous pale blue dot photograph was taken by Voyager 1 in 1990, when the spacecraft was at about 40 AU, near the outer edge of the Kuiper belt. Earth appeared as a sub-pixel point of blue-white light, barely visible in a beam of scattered sunlight. "That's here, that's home, that's us," Sagan said. The image became one of the most celebrated photographs in history. Voyager was at 40 AUs when that image was captured. The Oort cloud begins at roughly 2000 AU. From the inner edge of the Oort cloud, Earth would be 50 times smaller in the frame than it was in the pale blue dot, invisible, unreachable even by Voyager's instruments. From the outer edge, no instrument we've ever built could detect Earth at all. The Oort cloud is where the pale blue dot disappears. Sedna deserves specific attention because it's among the most puzzling objects ever found in our solar system, sitting at the doorstep of the Oort cloud in a way that challenges standard models of how the outer solar system formed. Discovered in November 2003 by astronomers Mike Brown, Chad Trujillo, and David Rabinowitz using the Palomar Mountain Observatory, Sedna was at the time the most distant solar system object ever detected. Its orbit is dramatically elongated. At perihelion, closest approach to the Sun, it sits at about 76 AU, already well beyond Pluto and the main Kuiper belt. At aphelion, its farthest point, it swings out to roughly 937 AU. Its orbital period is estimated around 11,400 years. At its current position, Sedna appears through the most powerful existing telescopes as a tiny reddish point of light with no resolvable surface features. Its diameter is estimated around 1,000 kilometers. Beyond that, direct observation can't tell us much. What makes Sedna extraordinary is its perihelion distance. At 76 AU, it sits completely outside Neptune's gravitational influence. Neptune can't have placed it there. But it's too close to the Sun for standard Oort cloud dynamics to have shaped it in the usual way. It occupies a region between the Kuiper belt and the Oort cloud that shouldn't contain objects with these properties, according to the standard model of solar system formation. The leading explanations involve a passing star during the Sun's early history, or the gravitational influence of the still hypothetical Planet 9, or some combination of early solar system dynamics that aren't fully understood. Whatever the explanation, Sedna signals that a region of the solar system between the Kuiper belt and the Oort cloud contains objects we've barely catalogued and was shaped by events 4.6 billion years ago whose full story hasn't been read yet. A second object with similar orbital characteristics, designated 2012 VP113, discovered by Scott Shepard and Chad Trujillo, confirmed that Sedna wasn't an anomaly. A class of objects sometimes called sednoids now exists in astronomers' catalogues, each one a signpost pointing toward the inner Oort cloud. Only 2 have been found so far. Models suggest hundreds or thousands more may exist, invisible to current survey technology. Planet 9 remains the outer solar system's most debated hypothesis. Proposed by Mike Brown and Konstantin Batygin in 2016, the idea holds that the clustering of several extreme outer solar system objects, including the sednoids, points to the gravitational influence of a large, undiscovered planet orbiting perhaps 200 to 800 AU from the Sun, roughly 5 to 10 times Earth's mass. As of 2024, Planet 9 remains unconfirmed. Direct observation hasn't found it. The statistical case for its existence from the clustering of known objects remains contested, with some researchers arguing it's a real signal and others attributing it to selection effects in how surveys have targeted the outer solar system. The Vera C. Rubin Observatory, built in Chile and expected to begin major sky survey operations around 2025, may settle the question. Its massive camera will image the entire southern sky repeatedly, finding objects previous surveys missed. Whether or not Planet 9 turns up, the resulting detailed map of the outer solar system will transform the available data for studying Oort cloud dynamics. The interstellar connection opened a completely new chapter when Oumuamua was detected in 2017. Its trajectory was unmistakably hyperbolic. It arrived from outside our solar system entirely. The first confirmed interstellar visitor ever detected, Oumuamua was elongated, reddish, and accelerated away from the Sun in a way that pure gravity couldn't fully explain, which generated significant scientific debate and a great deal of media coverage ranging from careful to irresponsible. The most widely accepted scientific explanations involve either a nitrogen ice fragment or a comet-like body, but the full picture isn't settled. 2 years later, Comet Borisov arrived in 2019 as the second confirmed interstellar object, and this one behaved exactly like a comet. It developed a proper coma and tail, confirming it was an icy body from another stellar system passing through ours. Material crosses between star systems. The interstellar medium isn't sterile. Objects ejected from other stars' outer comet clouds travel through interstellar space and occasionally pass through our solar system. Objects from our Oort cloud are almost certainly being ejected and traveling outward right now toward the interstellar medium. The same stellar encounter that brought Schultz's star within 52,000 AU of us 70,000 years ago likely ejected some of our Oort cloud objects outward, and those objects are currently somewhere in the interstellar medium, heading toward whatever stellar system they'll eventually reach. What this means is that the Oort cloud isn't just the edge of our solar system, it's the exchange zone, the interface between our gravitational domain and the larger galactic inventory of icy objects, the boundary at which our solar system participates in the slow mixing of stellar debris across the galaxy. The most isolated, cold, dark region of our solar system turns out to be, in a literal material sense, the most cosmically connected region we have. The Nemesis hypothesis is a useful case study in how the Oort cloud has inspired sweeping scientific speculation. In the 1980s, paleontologists noted what appeared to be a roughly periodic pattern in mass extinction events on Earth, with cycles of approximately 26 to 30 million years. Researchers proposed that the periodicity might reflect periodic comet bombardment, which in turn might reflect a regular perturbation of the Oort cloud, which in turn might reflect an undiscovered companion to our Sun, a second star, a brown dwarf, or a massive dark object on a very long elliptical orbit. Every 26 to 30 million years, this Nemesis object would pass through or near the Oort cloud, gravitationally disrupting it and sending a pulse of comets into the inner solar system. Some would hit Earth. Extinctions would follow. The hypothesis was studied seriously through the 1980s and early 1990s. Sky surveys looked for dim companion stars or brown dwarfs in the relevant regions. Nothing was found. As comprehensive surveys continued returning null results and the statistical case for extinction periodicity itself became more contested, Nemesis was gradually set aside. The hypothesis is now considered largely rejected, though it illustrated something real about the Oort cloud. Its sensitivity to external disturbances makes it a natural candidate for explaining anything catastrophic arriving from a cosmic source, and its enormous size means almost any massive perturbing object would leave its signature there. The galactic context of the Oort cloud is worth taking seriously for a moment, because it's rarely discussed and it reframes the cloud in an unexpected way. Our solar system occupies a position in the Orion arm of the Milky Way, about 26,000 light-years from the galactic center. One complete orbit around the galactic center, one galactic year, takes roughly 225 to 230 million years. The last time the Sun was in approximately its current galactic position, the Triassic period had just ended, and the first dinosaurs were appearing. That's one galactic year. As the solar system orbits, it also oscillates slowly through the galactic plane, the flat midplane of the Milky Way disk, on roughly 30 to 70 million year cycles, estimates varying by the model used. When the solar system sits in the galactic midplane, it's in a region of higher stellar density and more gas. Galactic tidal forces on the Oort cloud are also strongest there. The Oort cloud's perturbation environment changes as the solar system moves through the galaxy, with periods of higher and lower comet influx to the inner solar system depending on galactic position. This means comets aren't just coming from the Oort cloud randomly. They're coming from the Oort cloud shaped by a galactic environment that the solar system moves through continuously. The history of cometary bombardment on Earth is partly a history of where the solar system was in its galactic orbit at the time. The Oort cloud is the interface between our solar system and the galaxy writes in it constantly. The cometary chemistry angle connects the Oort cloud to life on Earth in ways that deserve specific attention. When an Oort cloud comet approaches the Sun and its surface begins to vaporize, the resulting coma, the glowing envelope of gas and dust surrounding the nucleus, can be enormous. Hale-Bopp's coma at peak extended over 500,000 kilometers across, larger in diameter than the Sun itself. That coma is a chemical inventory of what the comet carries. Water ice, expected and abundant. Carbon dioxide, carbon monoxide, methane, ammonia. But beyond these simpler compounds, telescopic analysis has revealed formaldehyde, methanol, ethanol, glycol, hydrogen cyanide, and a growing list of complex organic compounds. Material collected from Comet Wild 2 by NASA's Stardust mission, a short-period comet but representative of the same class of primitive icy bodies, contained glycine, the simplest amino acid, one of the building blocks of proteins. The chemistry that assembles amino acids was present in the original protoplanetary disk material that became comets, and it survived intact in cold storage for 4.6 billion years. Life on Earth appeared surprisingly rapidly after the late heavy bombardment ended roughly 3.8 to 3.9 billion years ago. The bombardment itself was a period of intense comet and asteroid impacts on the early inner solar system, triggered by a dynamical instability in the giant planet's orbits around 4 billion years ago. During this period, enormous quantities of cometary material struck Earth. Some of that material carried water ice, some carried organic compounds. The ocean you drink from and the amino acids in your proteins may have a partial cometary origin, with the Oort cloud serving as the long-term reservoir from which some of that material ultimately came. Whether cometary delivery was the primary pathway for life's ingredients to reach Earth remains an open and serious scientific debate. The deuterium to hydrogen ratio in cometary water doesn't perfectly match Earth's ocean water across all studied examples, which complicates a simple cometary delivery narrative. But the organic molecules are real, the delivery mechanism is real, and the timing of life's appearance after the bombardment ended remains striking. The Oort cloud was holding these ingredients for billions of years before Earth needed them. When it delivered, through the long chain of perturbation and orbital decay and cometary fall and impact, something that contributed to life's beginning, it was participating in the longest supply chain in history. The human relationship with comets across history adds a dimension that pure astronomy misses. Julius Caesar's assassination in 44 BCE was followed by a 7-day appearance of what became known as the Sidus Julium, interpreted by Caesar's supporters as his soul ascending to divine status. The Battle of Hastings in 1066 was preceded by Halley's Comet, depicted in the Bayeux Tapestry, with observers below looking up in obvious alarm. When Halley's Comet returned in 1910, newspaper coverage of the Earth's passage through the comet's tail, which did contain cyanogen, a toxic compound, at concentrations so dilute as to be completely harmless, generated genuine public panic in some quarters, with people selling protective comet pills and going to bed uncertain whether they'd wake up. The Heaven's Gate tragedy in March 1997 demonstrated the darker edge of humanity's psychological response to unusual celestial phenomena. All 39 members of the cult died in a mass suicide in San Diego, believing that a spacecraft was traveling behind Hale-Bopp and that physical death would free them to join it. The comet itself was obviously not responsible for what happened, but it illustrated how powerfully certain minds respond to an unexpected visitor in the sky, an appearance that defies the normal rules, something coming from the unknown dark. The grief around Comet Ison in November 2013 was different in character, scientific grief rather than mystical or tragic. Millions of people around the world had tracked Ison for months, watched its brightness predictions get updated, read the growing hope that it might be spectacular. When it disintegrated rounding the sun, the collective disappointment was real and widespread. People mourning a piece of frozen material 4.6 billion years old that had never known it existed, that had drifted in the dark since before Earth formed, and that fell apart in hours on its first and only pass through the inner solar system. The grief was genuine, and it says something about the human relationship with these objects. We give them names, we watch them, we feel something about what happens to them. The Oort cloud sends us these frozen envoys, and we respond to them with something that looks a lot like care. What the Oort cloud means for Earth's habitability is a question that doesn't get asked often enough. We occupy a solar system in the relatively quiet Orion arm of the Milky Way, far from the dense galactic center with its higher stellar density and more frequent gravitational encounters. Our Oort cloud, as a result, experiences fewer stellar disturbances per million years than the outer comet clouds of stars in denser galactic environments. The cometary influx to our inner solar system is relatively low. Stars in star clusters or near the galactic bulge are almost certainly sending more comets toward their planets, more frequently, with higher probabilities of extinction-level impacts on any life that might exist there. Our galactic address may be part of what makes Earth livable. The Oort cloud, positioned where it is, disturbed as infrequently as it is, may contribute to the relative calm that allowed complex life to develop and persist on Earth. The same structure that periodically sends extinction-level threats our way may, through its relative stability compared to other stellar systems, represent a net advantage. A large Oort cloud comet on a direct Earth impact trajectory would provide less warning time than a near-Earth asteroid. Asteroid surveys have been cataloging potentially hazardous objects for decades, providing years or decades of advance warning. A long-period comet from the outer solar system arrives faster and from any direction, potentially giving only months. A comet the size of Hale-Bopp striking Earth would represent an extinction-level event by any reasonable measure. The probability over any human lifetime is extremely low. Over geological time, it's happened before and will happen again. The Vera C. Rubin Observatory's All-Sky Survey may help by detecting incoming long-period comets earlier than previous systems. The warning time problem for Oort cloud comets won't be fully solved by any current technology. They can come from any direction and move quickly. But earlier detection creates more time for whatever response may be possible. The mathematics of what happens at the very edge of the Oort cloud says something specific about where our solar system ends and the galaxy begins. The Hill sphere of the Sun, the region within which the Sun's gravity dominates over the galactic environment's gravity, extends to roughly 100,000 to 200,000 AU. Beyond this boundary, objects are no longer meaningfully bound to the Sun. The galactic environment claims them. The Oort cloud fills essentially this entire Hill sphere, occupying the full extent of what our Sun can gravitationally hold. Objects in the outer cloud, at 100,000 AU, move at roughly 90 meters per second in their orbits, about the top speed of a Formula One race car, compared to Earth's orbital speed of 30 kilometers per second, which is more than 300 times faster. At these crawling speeds and enormous distances, orbital periods stretch to millions of years. One orbit at 100,000 AU takes roughly 10 million years. 10 million years ago, the first hominid primates were just beginning to appear in Africa. By the time an outer Oort cloud object in a circular orbit completes one trip around the Sun, our entire genus might have appeared, evolved, and been replaced by whatever comes next. Most Oort cloud objects aren't in circular orbits. They travel highly elongated paths that bring them much closer to the Sun at perihelion, spending most of their time out in the cold darkness. But the principle holds. The timescales of the Oort cloud operate on evolutionary, geological, galactic scales. Our entire recorded history, the 5,000 or so years from the first written records to the present, is a rounding error in the Oort cloud's rhythm. Proxima Centauri presumably has its own version of this structure extending in our direction, its own outer comet cloud reaching perhaps a light year or two toward us. Our outer cloud extends a light year or two toward Proxima. If both estimates are accurate, those outer clouds are relatively close to each other in the gap between the systems. During the relative motions of our Sun and Proxima through the galaxy over geological time, their outer clouds may have overlapped or interpenetrated. There may be a tenuous, essentially invisible gradient of loosely bound icy objects in the space between the two nearest stellar systems, some gravitationally attached to one, some to the other, some with no clear allegiance to either. The void between the stars isn't quite void, even if what's there is invisible at current instrument sensitivity and operationally irrelevant for any foreseeable mission. Stellar systems aren't sealed, isolated bubbles. Their outer comet clouds touch material exchanges between them. The interstellar medium is dotted with the refugees and castaways of planetary formation everywhere it has occurred in the galaxy. The organic chemistry angle connects to the deepest questions in science in a way that makes the Oort cloud feel less like an abstract astronomical feature and more like a chapter in the story of life itself. The total inventory of organic compounds locked in 2 trillion Oort cloud objects at a temperature within a few degrees of absolute zero, essentially perfectly preserved since the solar system's formation. That is the largest repository of primitive solar system chemistry in our immediate cosmic neighborhood. Formaldehyde, methanol, ethanol, hydrogen cyanide, amino acid precursors, all present in comets, which are the delivered samples of this greater inventory. When these compounds arrived on early Earth through cometary impact, they arrived in an environment that was already warm enough for liquid water, already supplied with energy sources, already capable of driving chemical reactions. The ingredients met the conditions. Something happened. Life appeared. The chain of causality from frozen Oort cloud object to living organism on Earth is real, even if we haven't traced every link in it yet. Every atom in your body has a history predating the solar system. The carbon was forged in stellar interiors that exploded as supernovae before the Sun formed. Some of the water passed through multiple molecular cloud environments before ending up in the disk that became our solar system. Some of that disk material spent 4.6 billion years in the Oort cloud before eventually becoming a comet, before eventually contributing to Earth's oceans or organic chemistry. The boundary between you and the frozen dark at the edge of the solar system is continuous. The same atoms, in different arrangements, at wildly different temperatures. Looking back across all of it, the scale, the population, the chemistry, the history, the comets, the human response, The Oort cloud reveals something about the nature of the universe that most science communication never quite lands. The universe is not human-sized. It was not built to be comprehensible on our timescales or in our units. The Oort cloud doesn't exceed human understanding as some exceptional case. It's actually one of the closer, smaller structures that exceeds it. The galaxy is 100,000 light-years across. The observable universe is 93 billion light-years in diameter. The Oort cloud, at less than 2 light-years, is a local feature, a neighborhood detail, and it already breaks the human mind's ability to hold it. That's the message. Not a pessimistic one, a clarifying one. The human mind is a remarkable thing, capable of mathematics and inference and deduction that reach past direct observation into domains that no eye could ever see. Jan Oort demonstrated that in 1950, sitting with cometry data and extending physical reasoning to infer a trillion-object structure nearly 2 light-years across, that he had absolutely no means to directly observe. And he was right. The universe is knowable, even in its coldest and most remote corners. The laws of physics apply everywhere, the mathematics holds everywhere, and careful reasoning can reach everywhere the evidence leads. The Oort cloud is a monument to that. Not to what we can't know, but to what we figured out from what we could observe. Not to the limits of science, but to its reach. And the reach of science being what it is, here we are, knowing that we're surrounded by a nearly 2 light-year sphere of frozen time, containing trillions of objects older than life on Earth, sitting at temperatures within a few degrees of absolute zero, being perturbed by the gravity of the Milky Way galaxy itself, occasionally sending messengers inward that cross the inner solar system in a blaze of light and then return to the dark. The Oort cloud is out there right now, in every direction, as you read or listen to this, surrounding the solar system in every direction for distances that make the solar system itself look negligible. This has been the case for 4.6 billion years. The Oort cloud was there before the first single-celled organism appeared on Earth, before the Cambrian explosion, before the dinosaurs, before the first hominids, before the first human, before the first civilization, the first city, the first written word. Through every plague and war and discovery and collapse and renaissance, through the entire history of everything anyone has ever known or thought or felt, and it will remain there, silent and cold and patient, for billions of years, after everyone currently alive is gone. Nobody tells you about this. Nobody explains how far it actually goes, or how many objects are out there in the dark, or what those objects have been through, or what they represent. The Oort cloud lacks the visual drama of Saturn's rings, the romantic draw of Mars, the exciting biosignature speculation of ocean moons. It can't be photographed, it can't be reached. Its scale defeats ordinary intuition so completely that explaining it feels like describing a color that doesn't exist. But it might be the most extraordinary single feature of our solar system, because what the Oort cloud tells us is this: the solar system we live in is not the tidy, poster-sized system of school diagrams. It's something vast and strange, and connected to the rest of the cosmos, in ways that took centuries of careful science to even begin to understand. The real solar system ends about halfway to the nearest star. Wrapped around everything we know, in every direction, for nearly 2 light-years, is a shell of frozen time. That's the Oort cloud. And now you know. If this landed for you the way it lands every time I sit with it properly, if there was a moment where the scale broke through and became genuinely felt, rather than just intellectually registered, drop a comment and tell me which moment it was. The Voyager numbers? The pale blue dot disappearing? The idea that the nearest star's outer cloud might be touching ours right now? The thought of comet Hyakutake being in transit for 70,000 years? Wherever the crack in your sense of scale happened, I want to know, because that's what this is for. The universe is this big, we live in this place, and it's worth actually feeling that, at least once. Now let's slow all the way down and really reckon with the formation story, because it's one of the most extraordinary things about the Oort cloud, the fact that it represents the very beginning. 4.6 billion years ago, where our solar system now exists, a molecular cloud drifted through the Milky Way, a vast, cold nebula of gas and dust, unremarkable by galactic standards, one of countless such structures in the galaxy. Something disturbed it, perhaps the shockwave from a nearby supernova detonation, perhaps the slow accumulation of its own gravitational weight acting over millions of years, and it began to collapse inward, The collapse accelerated the spin. Spinning faster, the cloud flattened into a disk, most of its mass concentrating at the center to form the proto-sun. The remaining material spread outward through the disk surrounding it. For the first several million years, this protoplanetary disk was hot, turbulent, and chaotic. Dust grains collided and stuck together, forming pebbles. Pebbles aggregated into boulders. Boulders merged into planetesimals, primitive bodies kilometers across that were themselves the building blocks of planets. Planetesimals collided and merged to form protoplanets, and eventually, 4 rocky planets formed in the inner solar system and 4 giant planets in the outer solar system. Not everything was incorporated. The disk held far more material than the planets could absorb, and the growing giant planets began exercising gravitational influence on an enormous scale. Jupiter, in particular, was a gravitational wrecking ball for the early solar system. Its mass, as it accumulated, sent enormous quantities of smaller bodies on new trajectories, some crashing into the young sun, some flung into the inner solar system to bombard the rocky planets, some ejected outward into the far reaches of the protoplanetary disk. Objects scattered outward in this way didn't simply escape the sun's gravity. Most settled into highly elongated orbits, ellipses stretching far out from the sun and then falling back in, and there they stayed for millions of years, tracing these long, looping paths through the cold outer solar system, while the planets continued to settle into their current configuration. What transformed these elongated, high-eccentricity orbits into the more circular orbits of the Oort cloud was the galaxy itself. The Milky Way's gravitational field doesn't just operate at the galactic center, it permeates the space around our solar system, and it's not perfectly uniform. The differential pull of galactic mass across the volume of the outermost solar system creates genuine tidal forces, working on timescales of hundreds of millions of years. These galactic tides pulled at the far ends of those elongated orbits and gradually raised the minimum approach distances, rounding the orbits out into the roughly spherical distribution that now surrounds us at every distance from 2,000 to 200,000 AU. The process wasn't fast by any unit of time a human brain can meaningfully process. It took hundreds of millions of years for the galactic tides to fully sculpt the cloud into something like its current form. During those hundreds of millions of years, the sun's birth cluster, the group of stars that formed from the same molecular cloud, gradually dispersed, the stars drifting apart on different orbital paths through the galaxy. During the period when neighboring young stars were still relatively close, their gravitational fields overlapped in the regions between them. Material could transfer. Icy bodies from neighboring young stellar systems could be gravitationally captured by the young sun and incorporated into its outer cloud. The Oort cloud may contain material from multiple stellar birthplaces. Objects floating in the dark at 100,000 AU might have formed around a different star, a star that has long since drifted thousands of light years away to some other position in the Milky Way. We are surrounded by what might be partially inherited material, collected during a period when the solar system's neighborhood was dense and active before the sun drifted to its current relatively quiet position in the Orion Arm. This inherited aspect of the cloud's character goes beyond historical curiosity. If Oumuamua and Comet Borisov demonstrated that material travels between stellar systems now, during the relatively calm interstellar medium of today, then the exchange was far more active during the sun's birth cluster period, when stars were much closer to each other. The Oort cloud is partly a product of that exchange. It is, at least in part, a collection inherited from a neighborhood that no longer exists in the form it had when the collection was assembled. The same process is presumably happening right now around young stars in active star-forming regions elsewhere in the galaxy. Those young stars are building their own Oort clouds, collecting material both from their own protoplanetary disks and from their neighbors. In a billion years, those clouds will be as fully formed and as isolated as ours is now, surrounding stellar systems whose planets may be just beginning to host whatever complex chemistry their environments allow. The Oort cloud, understood this way, isn't just our solar system's outermost structure. It's a record of a period in the solar system's history that no longer has any other surviving evidence. The birth cluster is long gone. The neighboring stars have scattered. The turbulent protoplanetary disk has resolved into the orderly solar system we inhabit. Only the Oort cloud preserves the character of that early period in frozen form, drifting in the dark at temperatures near absolute zero, holding objects that were sorted into their current positions by processes that completed billions of years ago. Let's do something that science communication rarely does with the Oort cloud. Walk through the actual mathematics in a way that carries emotional weight rather than just intellectual weight. One astronomical unit is 93 million miles. That's the Earth-Sun distance, and it's the yardstick. Everything scales off this. Voyager 1, after nearly 50 years of continuous travel since its September 1977 launch, sits at about 163 AUs as of 2024. That translates to approximately 15 billion miles. The signal it transmits home travels at the speed of light and takes about 22 hours to arrive at Earth. 15 billion miles, 22-hour signal delay. That's the farthest any human-made object has ever traveled. The greatest reach in history. The inner edge of the Oort cloud sits at roughly 2000 AU, or about 186 billion miles. If Voyager is at 15 billion miles now, reaching the inner edge would require traveling roughly 12 more times its current distance from the Sun. At its current speed of about 38,000 miles per hour, that journey would take about 300 years from this moment, 3 centuries to reach the beginning of the cloud. The outer edge at 100,000 AU is 9.3 trillion miles from the Sun. 9.3 trillion. Numbers of that magnitude don't register as numbers the way ordinary numbers do. The mind loses the ability to compare them to anything relatable. Consider this. If you began counting seconds from the moment of your birth and lived to the median human life expectancy, you'd count roughly 2.5 billion seconds. Not a trillion. You'd need to live 4,000 human lifetimes, counting every second continuously without sleep, to count to 9.3 trillion. That's how many miles it is from the Sun to the outer edge of our solar system. And the 9.3 trillion miles themselves are nearly empty. 2 trillion objects larger than a kilometer across are distributed through a sphere of this radius, each of them so far from its neighbors that a spacecraft traveling at Voyager's speed could pass through the entire cloud without ever coming within visual range of a single one. The density calculation is worth attempting. A sphere with a radius of 100,000 AU has a volume of roughly 4.2 times 10 to the 15th power cubic AU. 2 trillion objects in that volume gives an average of 1 object per roughly 2 million cubic AU of space. At that density, the average distance between neighboring objects in the Oort cloud is somewhere in the neighborhood of 120 AU, about 11 billion miles between any 2 adjacent objects. The Oort cloud is simultaneously the most object-rich structure in our solar system by total count, and the emptiest place in the solar system by anything resembling density. Traveling through it would feel like traveling through nothing. You'd know from the mathematics that you were surrounded by trillions of frozen objects. You'd feel nothing but the absolute cold, see nothing but stars, detect nothing on any instrument unless one happened to be within a few hundred miles of your position. The numbers say crowded. The experience would say completely empty. This is the strange character of the Oort cloud, described by numbers that suggest abundance, experienced as absolute void. The cometary flux, how many Oort cloud objects reach the inner solar system per year, gives some sense of the cloud's delivery rate over geological time. At any given time, approximately 2 to 3 new long-period comets are discovered each year. Automated sky surveys that scan for moving objects catch a fraction of what actually arrives, so the true rate of long-period comets entering the inner solar system is estimated at roughly 25 to 30 per year, passing within Jupiter's orbit. Most are faint. Only occasionally does one arrive large enough, bright enough, and well-positioned enough to become a naked-eye spectacle. 25 to 30 per year, continuously, for 4.6 billion years. That's a rough total of somewhere around 100 billion cometary arrivals to the inner solar system over the entire history of the solar system, the overwhelming majority of them arriving long before any eye existed to observe them. For billions of years, the Oort cloud was sending these deliveries inward, while Earth had no atmosphere, then while it hosted only single-celled organisms, then while it hosted only creatures without eyes. The comets came, struck what was there to strike, and left no observation in any record. Everything we've observed, named, catalogued, and celebrated represents a vanishingly small fraction of the total cometary history of our solar system. For every Hale-Bopp that became a cultural moment, billions of others arrived and departed without anyone knowing. The Oort cloud has been communicating with the inner solar system for 4.6 billion years, and we've been able to receive those messages for what amounts to a fraction of a second in the cloud's operating history. The human presence in this picture is fleeting in a way that even people comfortable with astronomical scale rarely sit with fully. We are, at most, a few 100,000 years removed from having any awareness of comets at all. Of that window, we've been scientifically capable of interpreting them for maybe 3 or 4 centuries. Of that period, we've understood what they actually are and where they come from for only 74 years. In the 4.6 billion year operating history of the Oort cloud, our awareness of it is a rounding error so small it can barely be expressed as a percentage. The cloud doesn't register this. It was here before us. It operates independently of our observation. When the last human civilization is gone, it will still be sending comets inward on its roughly 25 to 30 per year schedule, meeting now empty inner planets, swinging back outward, returning in millions of years to try again. The Oort cloud's timeline has no relationship to ours. We simply happen to be occupying a tiny window of it. Let's revisit the question of what it means to be in the dark at the outer edge of the cloud, this time with more physical specificity. In the outer Oort cloud, at 100,000 AU, the Sun's gravitational acceleration on an object is about 10 billion times weaker than it is at Earth's distance. An object in a roughly circular orbit at this distance moves at approximately 90 meters per second. 90 meters per second is the top speed of a Formula One race car. Earth travels around the Sun at 30 kilometers per second, which is 30,000 meters per second. The outer Oort cloud's objects are moving 330 times more slowly than Earth in its orbit. At 90 meters per second and a distance of 100,000 AU, completing one orbit takes approximately 10 million years. 10 million years ago, the ancestors of human beings were hominid primates in Africa. By the time an outer Oort cloud object in a roughly circular orbit completes a single trip around the Sun, our genus Homo will have appeared, evolved through perhaps a dozen species, reached some current form, and, statistically speaking, based on every other large mammal genus in Earth's history, probably gone extinct. The outer Oort cloud operates on evolutionary timescales, on geological timescales. The 5,000 years from the first Sumerian city-states to the present is 0.05% of one orbital period of an outer Oort cloud object. Most objects in the cloud aren't in circular orbits. They trace highly elongated ellipses that bring them far closer to the Sun at perihelion before swinging them back out to their aphelion distances. For these objects, the orbital mechanics are even more extreme. A body with a perihelion of 500 AU and an aphelion of 50,000 AU would have an orbital period of roughly 3 million years. 3 million years spans roughly the entire history of the genus Homo, from the first stone tools to the present. An Oort cloud object has had time to complete one orbit during the span it took for our ancestors to evolve from the first stone tool-using hominids to the current moment. That object is going around again right now, at the precise point in its 3 million year orbit corresponding to wherever it happens to be today, completely indifferent to the fact that the species that finally noticed it exists has gone from flint flakes to interplanetary spacecraft during its last single trip. The Oort cloud is not operating on our scale. It never has. We arrived very recently to a process that was already ancient and will be gone long before it ends. The philosophical dimension of this is worth spending time with rather than glossing over, because the Oort cloud offers something unusual, a genuinely comprehension-breaking scale that is also genuinely near to us in astronomical terms. Most structures that dwarf human comprehension are also cosmically remote. Distant galaxies, galaxy clusters, the cosmic web. Their incomprehensibility is partly a function of their distance. The Oort cloud is different. It begins approximately 186 billion miles from where we're sitting and extends outward from there. It is local. It is ours. It surrounds us right now, in every direction, as an immediate physical feature of our own solar system. And it's still completely beyond reach, completely invisible to us, operating on timescales that make the span of human civilization look like a brief weather event. There's a specific kind of intellectual vertigo that comes from properly considering the Oort cloud. Not the vertigo of distance, which is familiar from any discussion of cosmology, but the vertigo of scale, existing within something you thought was local, the discovery that home is much stranger and larger than you were told. Most people who've had any science education carry a mental model of the solar system as a comprehensible structure, planets in their orbits, distances that can be represented on a single page, a system that fits inside a concept. The Oort cloud doesn't fit inside a concept. It defeats the model completely, replacing a comprehensible system with something that is almost entirely nothing, stretching almost to the nearest stars, containing trillions of frozen objects nobody has ever seen. The realization that this is what our solar system actually is, not the school poster version with the planets neatly spaced, is something that, when it lands properly, tends to be permanent. The comfortable mental model doesn't fully reassemble. The solar system feels different afterward, bigger and stranger, and more connected to the wider universe than it seemed before. That experience of permanent reframing is one of the things good science communication aims for, and the Oort cloud offers it more reliably than almost any other topic in astronomy, because the gap between the conventional picture and the reality is so enormous. Let's consider the question of direct exploration one more time, because technology is changing and the future of Oort cloud science, while still distant, is not entirely static. No mission has ever been sent toward the Oort cloud. No mission currently in development has any realistic prospect of reaching it in a timescale any institution can plan for. The physics is simply too unfavorable with current technology. Voyager 1, traveling for nearly 50 years at 38,000 miles per hour, is at 163 AU. The inner Oort cloud begins at 2000 AU. The travel time math doesn't improve enough with any propulsion system that currently exists or can currently be built. Solar sails represent one candidate for dramatically higher speeds. A spacecraft with a very large, very lightweight sail could use sunlight pressure for propulsion, and by approaching very close to the sun first, getting a concentrated burst of radiation before heading outward, could potentially reach speeds far higher than any rocket. Experimental solar sail missions have been tested in Earth orbit. The Icaros spacecraft launched by JAXA in 2010 was the first to successfully demonstrate solar sailing in interplanetary space. The Planetary Society's Light Sail 2 successfully demonstrated controlled solar sailing in low Earth orbit in 2019. These are proofs of concept, not deep space exploration vehicles, but the technology is real and advancing. Laser propulsion takes the concept further. A ground-based or space-based laser array could, in principle, push a very lightweight sail-equipped spacecraft to a much higher fraction of the speed of light than solar pressure alone could achieve. The Breakthrough Starshot initiative, announced in 2016 and backed by significant private funding, proposed this concept for eventual interstellar missions. Small spacecraft pushed by powerful lasers to perhaps 20% of the speed of light. At that speed, the inner Oort cloud would be reachable in hours rather than centuries. The engineering challenges are enormous. The laser array needed would require power levels and precision that are far beyond current capability. The spacecraft would need to survive acceleration, survive transit through the interstellar medium at significant fractions of light speed, and somehow return or transmit data. These aren't problems with obvious near-term solutions, but the concept is physically plausible, which is more than could have been said of interplanetary travel a century ago. Even if laser propulsion becomes practical, reaching the Oort cloud for science would require decelerating at the destination, which is much harder than accelerating. A spacecraft that has been pushed to 20% of the speed of light by a laser can't easily be slowed down again without a second laser array at the destination end, or without some form of onboard propulsion that would massively increase the spacecraft's mass and counteract the whole premise of a lightweight sail. These are solvable problems in principle. Whether they're solvable in any time frame a currently existing civilization would recognize as plannable is much less certain. The Oort cloud may remain beyond human reach for a very long time, not because the physics forbids it, but because the engineering gap is genuinely large. In the meantime, indirect science continues to advance. Each new long-period comet that arrives in the inner solar system is a free Oort cloud sample delivery. As spectroscopy becomes more sensitive and survey technology finds more long-period comets at greater distances, the the science extractable from cometary arrivals improves. The Vera C. Rubin Observatory's Sky Survey, expected to run for a decade starting around 2025, will find enormous numbers of previously unknown small bodies and potentially many more long-period comets at earlier stages of their infall, giving longer observation windows and better orbital determination for objects that were previously discovered too close to perihelion for comprehensive study. The interstellar objects angle adds another dimension. If Oumuamua and Borisov represent the first two confirmed interstellar visitors ever detected, improved survey technology will likely detect many more. Each one is a sample from another star system's equivalent of our outer solar system, a package of chemistry and mineralogy from another stellar environment, arriving for study without the need for any mission to travel there. The Rubin Observatory and subsequent generations of sky surveys may turn the detection of interstellar visitors from a once-per-decade event into a routine annual occurrence. What this means for astrobiology is particularly worth considering. If interstellar objects carry organic molecules, as our own comets demonstrably do, and if such objects arrive in planetary systems at regular intervals, then the exchange of organic chemistry between stellar systems is an ongoing process happening throughout the galaxy. Life's precursor molecules are not confined to the stellar system in which they originally formed. They travel. They've been traveling since the first cometary objects were ejected from the first planetary systems that formed in the early universe. The Oort cloud, viewed in this galactic context, is one node in a vast, slow network of chemical exchange. Material that entered our Oort cloud 4.6 billion years ago, preserved in frozen form, eventually delivered to Earth as a comet, may have contributed to the origin of life. Material that the Oort cloud has ejected over its history, sent outward by gravitational encounters, lost to interstellar space, may be arriving right now at another stellar system, contributing to whatever chemistry that system's planets are running. The flow is continuous. The network is galactic in scope. The timescales are geological. We are part of this network. Earth is a participant in the exchange, both as a receiver of incoming material and as the home planet of a species that has now launched physical objects, some of which, like Voyager 1, are already in interstellar space, carrying Earth chemistry outward. The network that was purely natural for 4.6 billion years now includes one node that is partially deliberate. The Oort cloud is the mechanism by which our solar system participates in this exchange. It's the reservoir that gives and receives. It's the interface between our gravitational domain and the wider galaxy, and it's been operating in this capacity, silently and patiently, since long before any living thing on Earth was complex enough to wonder where the universe began. The cometary chemistry section deserves more space than we've given it, because the specific inventory of molecules found in comets keeps expanding with each mission and each improved spectroscopic analysis, and the list is genuinely astonishing. When a comet's coma is analyzed spectroscopically, the light from the coma broken into its component wavelengths, each wavelength corresponding to specific molecules, the results have consistently exceeded expectations. The early inventory was relatively simple: water, carbon monoxide, carbon dioxide, methane, ammonia. These are the expected volatiles of the cold outer solar system, the compounds that couldn't condense near the young warm sun, and instead ended up in the frozen outer regions. As instruments improved and more comets were studied, the list expanded dramatically. Methanol, the simplest alcohol, was detected. Ethanol, the alcohol in beverages, was detected. Formaldehyde was confirmed in multiple comets. Glycol, a compound with industrial uses here on Earth. Hydrogen cyanide, a toxic compound from an Earth survival perspective, but a key precursor to amino acid synthesis from a chemistry perspective. Acetaldehyde, formic acid, acetic acid. The organic inventory of comets now fills pages of chemical tables. The Rosetta mission's extended study of Comet 67P from 2014 to 2016 returned detailed chemical data that expanded the list further. Molecular oxygen was detected in the comet's coma, a surprising finding because molecular oxygen is reactive and wasn't expected to survive in the comet's composition for 4.6 billion years. Glycine, the simplest amino acid, wasn't found directly in 67P's coma during Rosetta, but had been found in samples returned from Comet Wild 2 by the earlier Stardust mission. Phosphorus, a key element in DNA and cell membranes, was detected in 67P's coma as well. The list of molecules needed for life, amino acids, nucleobases, sugars, lipids, phosphates, has individual molecular precursors represented in cometary chemistry for most categories. The full building blocks aren't there in assembled form. Comets aren't carrying pre-made proteins or DNA. But the precursor molecules that, under the right conditions and with the right energy sources, can assemble into those structures, those are present. And the conditions on early Earth were the right conditions, with the right energy sources. Volcanic heating, ultraviolet radiation from the young sun, lightning in the early atmosphere, hydrothermal vents on the young ocean floor. These were all available energy sources capable of driving chemical synthesis. The delivery of cometary organic material into this environment is, from a chemistry standpoint, a reasonable pathway to the origin of life's precursors. Whether it's what actually happened remains the central open question in astrobiology. The alternative view, that life's organic precursors were synthesized entirely on Earth from simpler atmospheric and geological chemistry without cometary contribution, is also chemically plausible and has its own substantial body of supporting evidence. The two pathways aren't mutually exclusive. Both may have contributed, but the Oort cloud's role in the story of life, as the long-term cold storage for the early solar system's organic chemistry, the reservoir from which cometary deliveries were made, is part of the conversation regardless of which pathway predominates. The numbers that make this tangible, during the late heavy bombardment period, roughly 3.9 to 4 billion years ago, the rate of cometary and asteroid impacts on Earth was dramatically higher than it is today. The total mass of material delivered to Earth during this period, mostly from the destabilized outer solar system, meaning a significant cometary contribution, was enormous. The material included water ice and organic compounds. Earth's current oceans hold roughly 1.4 billion cubic kilometers of water. Even a small percentage cometary contribution during the bombardment represents a vast quantity of delivered water and chemistry. The Oort cloud has been emptying itself, very slowly, at the rate of 25 to 30 long-period comets per year to the inner solar system, for 4.6 billion years. The total delivery over that period, measured against what the cloud currently contains, is a small fraction of its total population. The cloud is not meaningfully diminished by 4.6 billion years of cometary loss to the inner solar system. It's still out there, still containing trillions of objects, still conducting its slow business of perturbation and delivery. And the business continues. Right now, at this exact moment, as you're reading or listening to this, several objects somewhere in the Oort cloud have been perturbed onto trajectories that will eventually carry them into the inner solar system. The perturbation may have happened decades ago, or thousands of years ago, or millions of years ago. The objects are in transit. Their paths are set by the gravitational nudge they received and the orbital mechanics that have been operating since. They don't know they're comets yet. They're not close enough to the sun for any vaporization to occur. They're still just frozen objects, drifting in the dark, falling imperceptibly slowly at first, then gradually faster as the sun's gravity gains authority over them. In tens of thousands of years, or hundreds of thousands of years, or a million years, some of them will cross into the inner solar system. They'll develop comae and tails. They'll blaze bright against the night sky. Whatever intelligence exists on Earth at that time will look up and see them, and perhaps know what they are and where they came from. Or perhaps not. Perhaps the Earth at that time will have no observers. The geological record is not optimistic about the long-term survival prospects of any particular species or civilization. Either way, the comet will arrive. The Oort cloud will have made another delivery. The process will continue as it has always continued, indifferent to whether anyone is watching, indifferent to whether the inner solar system contains planets capable of hosting life, indifferent to everything except the physics that has governed it since the beginning. The Oort cloud is, in the end, a kind of ultimate fact about where we live. Not a fact that changes anything about daily life, not a fact that solves any problems or creates any new ones in any immediate sense. Just a fact about the true size of our solar system, the true age of the material surrounding us, the true nature of our position relative to the stars. We live at the center of a nearly 2 light-year sphere of frozen time. We are surrounded, in every direction, by trillions of objects older than life on Earth, sitting at temperatures within a few degrees of absolute zero, connected to the wider galaxy by gravitational forces that operate on timescales we can barely name. The nearest star is less than 5 light-years away, and our solar system's gravitational influence reaches roughly halfway to it. That's not a small thing to understand about the place you live. The Oort cloud is out there. It has been out there for 4.6 billion years. It will be out there for billions more. And embedded in it, preserved in frozen form, is the chemistry of our solar system's beginning, the record of where the planets came from, what forces shaped the early solar system, what the raw material looked like before anything organized into the familiar structures we know. Every comet the Oort cloud sends us is a message from that beginning. An ice sample from the origin, a chemical letter written 4.6 billion years ago and only now being opened. Nobody tells you this is how vast it is. Nobody explains that the entire solar system as you picture it, the sun, all 8 planets, everything, sits inside a structure so large that light takes nearly 2 years to cross it. Nobody tells you there are 2 trillion frozen objects out there in the dark, each one older than the oldest rock on Earth. Now you know. And the universe, I think, is a little more real for it. One more angle worth sitting with, because it reframes the Oort cloud in a way that most people never consider. What it means that this structure is invisible to us. Most of what astronomy identifies as important can be seen. The sun, the planets, even distant galaxies. Each of these can be observed directly, either with the naked eye, through a telescope, or in photographs taken by telescope. Distant objects like the Andromeda Galaxy, at 2.5 million light-years, remain visible to the naked eye from a dark site on a clear night. The visible universe is vast, and yet much of it is accessible to some form of direct observation. The Oort cloud is different. No object within it has been directly imaged in its natural, undisturbed state. No photograph shows the cloud's population. No artwork represents it with accuracy, because we don't know enough about the spatial distribution of its objects to draw it truthfully. Its existence is known entirely through inference, from the behavior and orbital characteristics of the comets it sends into the inner solar system, from mathematical models of how the early solar system would have distributed material, from the physical impossibility of explaining long-period comets without a vast spherical source. This places the Oort cloud in interesting company. Dark matter, the hypothetical substance thought to constitute a large fraction of the universe's mass, is also inferred rather than directly observed. The cosmic web of filaments, connecting galaxy clusters across cosmic scales, is known from gravitational evidence and computer simulation, not from any photograph. Some of the most consequential structures in the universe are known not because we can see them, but because the things we can see make no sense without them. The Oort cloud is the local version of this. It's the invisible structure that surrounds everything visible in our solar system. It's the dark matter of our immediate neighborhood. Not literally dark matter in the technical physics sense, but dark in the sense that it escapes detection, that it is known by inference rather than image, that it envelops the solar system we can see without being visible itself. What this demonstrates is that reality is not contingent on observability. The Oort cloud was there before any instrument capable of detecting it existed. It was there before any being capable of looking for it existed. Its reality required no witness. It simply was, and continued to be, and sent comets inward, and received stellar perturbations, and slowly evolved over billions of years without any acknowledgement from the solar system's inner regions. We came late to the knowledge of it. Jan Oort, in 1950, was, as far as we know, the first entity in the history of the universe to understand that the Oort cloud exists. In 4.6 billion years of the cloud's operation, 4.6 billion minus about 74 years passed before any mind anywhere grasped what it was. That's an almost comical asymmetry. 4.6 billion years of operation, and then a Dutch astronomer, with a pad of paper and some orbital data, figured out the whole thing in what probably amounted to a few months of concentrated work. The universe had been keeping this secret for 4.6 billion years, and it wasn't exactly making it hard to find. The evidence was in the comets. The comets were in the sky. The sky had been watched by human beings for thousands of years. But the synthesis, the leap from cometary arrival patterns to a spherical outer reservoir, waited until 1950. For most of human history, People watched the Oort cloud's messengers arrive without the slightest idea where they came from. Ernst Öpik got to the hypothesis first in 1932, which is a detail worth holding on to. Two astronomers, working independently, arrived at essentially the same conclusion within 18 years. The evidence was pointing at the Oort cloud clearly enough that once the right questions were being asked, the answer was almost overdetermined. Once someone looked at the orbital distribution of long-period comets and asked, where must these be coming from? The spherical reservoir was the only defensible answer. The Oort cloud had been writing the answer on the sky for billions of years, waiting for someone to read it correctly. The scientific method, applied with patience and care to data that had been accumulating for decades, reached out into a domain no telescope could touch and found something real there. That's worth celebrating, not just as an astronomy achievement, but as a demonstration of what inference-based knowledge can do. We don't need to touch everything to know it. We don't need to see everything to understand it. The fingerprints of a vast structure, read carefully enough in the things we can see, can reveal the structure itself. The Oort cloud is fully consistent with everything else we know about physics, orbital mechanics, solar system formation, and galactic dynamics. It doesn't require any new physics. It doesn't demand any exotic explanation. It falls naturally out of the same physical laws that govern everything else in the solar system, applied to the enormous distances of the outer solar system over the enormous timescales of the solar system's age. The Oort cloud is strange, not because the physics is strange, but because the scales involved, the distances, the object counts, the timescales, exceed what the human mind was built to handle. We were built to navigate landscapes, to track the positions of prey and predators, to remember the faces of maybe 150 to 200 people, to plan on timescales of years, or at most decades. The Oort cloud requires holding in mind a structure 200,000 AU across, containing 2 trillion objects, 4.6 billion years old, operating on cycles of millions of years. None of our evolved mental tools were built for that. We have to do it through mathematics and reason and metaphor, and the conscious effort to extend our intuition beyond its natural range. The effort is worth making, not because it changes anything practical about your life, not because understanding the Oort cloud will make you better at your job, or more attractive to potential partners, or more resilient in difficult circumstances, but because the universe is this way, and you live in it, and knowing what it actually is seems like a reasonable priority for any mind that has the opportunity to find out. The Oort cloud is the real edge of our solar system, the true boundary of the sun's gravitational domain, the outermost reach of the place we call home, and it is so far, so cold, so vast, and so full of frozen time that even the most practiced astronomical imagination strains to contain it. But it's out there, in every direction, right now. That fact, sitting with it fully, is one of the stranger and more clarifying experiences available to a curious human mind. The Oort cloud, vast enough to surround a solar system and reach halfway to the next star, old enough to predate life on Earth, full enough to contain 2 trillion frozen objects, cold enough to preserve 4.6 billion-year-old chemistry intact, and real enough that every comet you've ever heard of, every spectacular naked-eye display, every blazing tail across the winter sky, was a delivery from this frozen dark. The next time you see a comet, even a faint one, even just a smudge in binoculars on a clear night, you're seeing a message that has been in transit for tens of thousands or millions of years, from a place almost incomprehensibly far from anything you've ever experienced, delivered by forces operating on galactic timescales, briefly lit by a star that is itself a small and unremarkable member of a galaxy containing hundreds of billions of others. The Oort cloud sends those messages constantly. Most of them we're not looking up to receive, but every once in a while, a comet arrives bright enough to stop someone in their tracks, and they look up, and for a moment, they're connected to something 4.6 billion years old, drifting in from the edge of the solar system, briefly part of the world they can see. That moment, that connection, is real. The frozen object that made it happen has been traveling toward that moment for longer than anything on Earth has existed, and the Oort cloud that sent it has been waiting just as long, surrounding us in the dark, full of trillions more messages that haven't been sent yet. That's the Oort cloud, and now it's yours to know. The history of humanity's relationship with comets is worth tracing more carefully than we usually do, because it runs parallel to everything else that makes the Oort cloud interesting. Every comet that has appeared in human skies was an Oort cloud delivery. Every fear, every wonder, every calculation, every myth associated with comets over the last several thousand years was a human response to something that originated in the frozen dark 2,000 to 200,000 AU away, set in motion by a galactic tide or a passing star, and fell inward for hundreds of thousands or millions of years before arriving to become a cultural event. Julius Caesar's assassination in 44 BCE was followed within days by the appearance of a comet that blazed in the Roman sky for 7 consecutive days. Caesar's supporters called it the Sidus Julium, the Julian star, and interpreted it as Caesar's soul ascending to heaven. It was used as political evidence for Caesar's divinity and became a significant part of the mythology surrounding Augustus's legitimacy as Caesar's heir. The comet, a real astronomical event, carefully recorded by Roman and Chinese observers alike, became entangled in one of the most consequential political transitions in Western history. An Oort cloud object, or possibly a Kuiper Belt comet, arrived at a politically charged moment and became part of the founding mythology of the Roman Empire. The Bayeux Tapestry, woven in the 11th century to commemorate the Norman conquest of England, depicts Halley's Comet in extraordinary detail. The tapestry shows Harold Godwinson on his throne, looking up at the comet with a visible expression of concern or dismay, while a group of men below him point up at it. The Latin inscription translates roughly as, "These men marvel at the star." Halley's Comet appeared in April and May of 1066, several months before the Battle of Hastings in October. The comet was read by English observers as an omen. The Normans used it as a sign of divine favor for William's cause. The same astronomical event, the same Oort cloud, or more precisely Kuiper Belt object, was interpreted by opposing sides as supporting opposite conclusions, both of them supernatural. What it actually was is a ball of ice and rock about 15 kilometers across, going about its 75-year orbital business, briefly illuminated by solar radiation as it swung through the inner solar system for the 28th or 29th time since humans began keeping written records. The 1910 return of Halley's Comet produced a different kind of cultural event, one that tells us something specific about how science and public perception interact. Astronomers had detected cyanogen, a compound related to cyanide, in the comet's tail. News reports, ranging from accurate to sensationalized, communicated this fact to a public that didn't have the tools to evaluate what it meant. The Earth would pass through the comet's tail, some papers noted. The tail contained a toxic substance, other papers confirmed. What the papers often failed to communicate adequately was that the tail, while chemically interesting, was so vanishingly diffuse, a better vacuum than anything achievable in a laboratory on Earth, that no meaningful quantity of cyanogen could ever reach Earth's surface or atmosphere. The effect on Earth's inhabitants would be, and was, precisely zero. Nevertheless, the panic was genuine in some quarters. Entrepreneurs sold comet pills as protection. Some families spent the night of the Earth's passage through the tail in sealed rooms with damp cloths under the doors. Newspaper archives from the period document genuine fear in the general population about whether morning would arrive. Morning arrived. The comet's tail passed over Earth, and the only consequence was that astronomers measured its chemical composition more precisely than ever before. But the episode illustrated something about the human relationship with comets that has been true for as long as human records exist. These objects, with their unpredictable appearances and their dramatic tails, trigger a deep psychological response that logic and astronomical explanation can struggle to fully override. The Heaven's Gate tragedy in March 1997 is the darkest example in modern history. The group's founder, Marshall Applewhite, had taught his followers that a UFO was traveling in the wake of Hale-Bopp, and that the members' physical bodies were containers from which their souls could be freed to join the spacecraft if the bodies were abandoned. All 39 members of the group died in a planned, deliberate mass suicide in their house in Rancho Santa Fe, California, the largest such event in American history. The comet itself, blazing at peak brightness in the April sky visible from Southern California, was not responsible for what happened. The tragedy was the result of years of ideology and psychological influence, and would not have required a comet to occur. But Hale-Bopp's timing and visibility brought the group's beliefs to a crisis point. The Oort cloud delivered a spectacular object, as it sometimes does, and a particular group of human beings responded in the most extreme possible way. The anticipation and disappointment surrounding Comet Ison in 2013 was nothing like the Heaven's Gate situation in character, but it showed the same underlying reality. People form emotional relationships with comets. Ison was a first-time visitor from the outer solar system, discovered in September 2012 using the International Scientific Optical Network telescope in Russia, and early photometric data suggested it might become spectacularly bright as it approached the Sun. Amateur astronomers tracked it for over a year. Astronomy websites published brightness predictions updated weekly, then daily. The phrase, "Comet of the Century," appeared in media coverage, always qualified, always hedged, but present. Some projections suggested Ison might remain visible in daylight after perihelion. Forums filled with imaging plans and observation strategies. People bought telescope accessories specifically for Ison. The collective attention directed at a frozen object 4 to 5 AU away, still months from the Sun, was substantial and real. When Ison disintegrated on November 28, 2013, passing within about 1.2 million kilometers of the solar surface, the collective reaction among the astronomy community and its extended audience was palpable disappointment. Social media, still relatively young as a medium for public science engagement, captured the emotion in real time. Astronomers who had been following Ison for over a year expressed feelings that, from a certain distance, looked surprisingly similar to grief. A piece of frozen material 4.6 billion years old, making its first and last pass through the inner solar system, fell apart in the Sun's heat, and tens of thousands of people who had never met this piece of frozen material felt something genuine about it. That emotional response, which is real, and which probably most people reading this or listening to this have experienced in some form with some comet or some other astronomical event, points to something important about the human relationship with the Oort cloud. We can't see it, we can't reach it, we will not visit it in our lifetimes, or probably in the lifetimes of anyone alive today, and yet it sends us these temporary visitors, and we name them, and we watch them, and we feel something when they arrive and when they're gone. The Oort cloud doesn't care about any of this. The emotional weight we attach to its deliveries is entirely our contribution, not its. But the fact that we respond this way, that a ball of ice from 100,000 AU away can provoke genuine feeling in human beings, says something about the relationship between our minds and the cosmos. We're not dispassionate observers of astronomical events. We're participants, in the sense that our mental and emotional lives are shaped by what we see in the sky. The sky has always done this to us, and the Oort cloud is the most remote, most ancient source of what the sky shows us. When you understand the Oort cloud fully, when the 2 light-year extent lands, when the 2 trillion object population becomes real, when the 4.6 billion year age connects to everything you know about Earth's history, what you're really doing is extending your understanding of where you live. Not just, I live on Earth in the solar system, but I live at the center of a nearly 2 light-year sphere of frozen time, which is itself embedded in the Orion arm of the Milky Way galaxy, which is one of hundreds of billions of galaxies in the observable universe. That's the full address. Most people never get to all of it. The Oort cloud is the part of the address that extends past the comfortable part, past the planets and asteroid belts and Kuiper belt, into the surrounding darkness that is technically home, but experientially unimaginable. And knowing your full address, even the parts you'll never visit, even the parts that exceed the mind's natural grasp, is something worth having. The Oort cloud is out there. It's been out there for 4.6 billion years. The next comet it sends us is already in transit, somewhere between 2,000 and 100,000 AU away, falling silently toward a future appointment with the inner solar system, and whatever civilization, if any, will be looking up when it arrives. The universe keeps sending messages from the edge of everything familiar. The least we can do is learn to read the return address. The question of planetary defense sits at the intersection of the Oort cloud's beauty and its danger, and it's worth spending time there, because the threat profile of a long-period comet is meaningfully different from that of an asteroid, and most public discussions of planetary defense focus almost entirely on asteroids. The asteroid threat is real, and it has been studied in increasing depth over the last 3 decades. Near-Earth asteroids, Rocky bodies whose orbits bring them close to Earth's path can be catalogued, tracked, and in principle deflected with enough warning time. NASA's Planetary Defense Coordination Office maintains running catalogues of known near-Earth objects. Missions like DART, which successfully altered the orbit of an asteroid called Dimorphos in September 2022, have demonstrated that kinetic deflection is technically possible. The warning timescales for known asteroid threats can be years, decades, or centuries. Enough time, at least in principle, to plan and execute a response. Long-period comets from the Oort cloud operate on entirely different terms. Most of them are not in any catalogue, because most of them have never entered the inner solar system before, and thus have never passed close enough to Earth for our surveys to detect them. The first indication that a new long-period comet is inbound typically comes when it crosses inside the orbit of Jupiter, roughly 5 AU from the Sun, at which point it has begun outgassing sufficiently to appear in telescope surveys. From that point to closest approach to Earth might be anywhere from several months to a few years, depending on the specific orbital geometry. For a large, fast-moving comet on a steep inbound trajectory, the warning time could be less than a year. That's a problem, because a year is not a lot of time to plan and execute a deflection mission for an object that might be tens of kilometers across, traveling at tens of kilometers per second. Hale-Bopp, as it appeared in 1997, was estimated at roughly 60 kilometers in diameter, making it one of the largest comets observed in the modern era. An impactor of that size striking Earth would not be a regional catastrophe. It would not be a national catastrophe. A 60-kilometer object hitting Earth at comet velocities releases energy on a scale that ends geological eras, that ends species. The last time something even roughly comparable struck Earth was 66 million years ago, and the aftermath reshaped the planet's biosphere permanently. Hale-Bopp passed safely. Its closest approach to Earth in 1997 was about 197 million kilometers, not especially close by astronomical standards. But it serves as a useful thought experiment for what the Oort cloud is capable of delivering. Not every long-period comet will arrive on a safe trajectory. Orbital mechanics distributes their paths across all possible geometries, and some fraction of them, over geological time, will intersect with Earth's position. The geological record confirms this has happened. The question for the current era is whether humanity can build detection and response systems fast enough and capable enough to handle a threat that might arrive with minimal warning. The Vera C. Rubin Observatory, which began science operations in 2025 in Chile, represents the current generation's most powerful tool for addressing this. With an 8.4-meter primary mirror and a camera capable of imaging the entire southern sky every few nights, Rubin will detect enormous numbers of previously unknown solar system objects over its 10-year survey. Its cadence, returning to the same patches of sky repeatedly, building up time-domain data on moving objects, is precisely calibrated for finding things that weren't there before, including inbound comets. Rubin won't solve the warning time problem for the fastest, steepest cometary inbound trajectories, but it will substantially increase the fraction of long-period comets detected early enough to allow meaningful response planning. That's progress. Not a solution, but progress, which is what the realistic version of planetary defense looks like. What makes the Oort cloud comet threat categorically different from the asteroid threat isn't just the warning time, it's the physics of the objects themselves. Asteroids, even the largest, are rocky bodies with densities comparable to stone or metal. Long-period comets from the Oort cloud are predominantly ice and dust, often described as dirty snowballs, and they can be much larger than almost any asteroid that crosses Earth's orbit. Hyakutake, which passed within 15 million kilometers of Earth in 1996, an uncomfortably close visit by solar system standards, was roughly 2 kilometers across. Hale-Bopp, arriving 1 year later, was estimated at 60 kilometers. The size range possible in the Oort cloud encompasses objects that would rank among the most destructive impactors in Earth's geological history if they arrived on a collision course. And their velocity at perihelion, driven by the long fall from the outer solar system, routinely exceeds 30 kilometers per second, several times faster than a typical near-Earth asteroid, which means several times more kinetic energy per unit of mass. The combination of potential size and high velocity makes Oort cloud comets the most energetic potential impactors in the solar system, and the most difficult to address with existing planetary defense approaches. Detection early enough to enable a response is therefore not just a scientific goal, but a civilizational one. The deeper problem, what you actually do once you've detected an inbound object with limited warning time, remains genuinely unsolved. Kinetic impactors work well when you have years of lead time and a relatively small target. Nuclear standoff detonations, which are more controversial but potentially more effective for large objects on short timelines, exist as theoretical options but have not been tested. Gravity tractors, spacecraft that hover near an object and gradually pull it off course with their gravitational influence, require timescales of years to produce meaningful trajectory changes. The honest assessment, as of the mid-2020s, is that humanity has the beginnings of a planetary defense capability against the asteroid threat, and essentially no proven capability against a fast-moving, large, previously unknown, long-period comet with under a year of warning. This isn't a reason for panic. The rate at which civilization-threatening comets arrive from the Oort cloud is very low on any human timescale. The geological record suggests impacts of the largest scale occur on intervals of tens of millions of years. But the probability is not zero, and the consequences of being caught unprepared would be final. The Oort cloud, for all its beauty and scientific fascination, is also the solar system's largest reservoir of potential extinction-level threats. It holds this status not maliciously, the physics doesn't operate on intentions, but as a simple consequence of containing 2 trillion objects, some of them very large, some of them on trajectories that will eventually send them inward. The interstellar objects, Oumuamua, which passed through in 2017, and Borisov, which arrived in 2019, introduced a category of object that the planetary defense community is still working to fully integrate into its threat models. An interstellar object, by definition, arrives from outside the solar system with a velocity exceeding solar escape velocity. It cannot be gravitationally captured. It makes one pass through the inner solar system and continues outward. The warning time for such an object, if it were on a collision course with Earth, would likely be far shorter than even that for a fast-moving Oort cloud comet, potentially weeks or months. Borisov was detected when it was still outside Jupiter's orbit, giving astronomers several months to study it, but its trajectory never brought it close to Earth. A similar object on a threatening trajectory might be detected with far less lead time. None of this is to suggest that the sky is about to fall. It's to suggest that the Oort cloud and the broader outer solar system represent an aspect of humanity's long-term situation that deserves more serious attention than it typically receives in public discourse. The conversations about existential risk tend to focus on things happening right now: AI alignment, pandemic preparedness, nuclear arsenals. These are real concerns. But the Oort cloud has been operating on its delivery schedule for 4.6 billion years, and it will continue operating on that schedule regardless of what humanity does internally. Building the detection infrastructure and response capabilities to address the rare but non-negligible threat from the outer solar system is a genuinely important long-term project, and the scientific community working on it deserves support. The future of exploration at Oort cloud distances represents one of the most ambitious frontiers in all of science, and the honest answer is that we are a very long way from it. Voyager 1, the fastest spacecraft ever launched by humanity, has been traveling for more than 50 years and sits at roughly 163 AUs from the Sun. At that rate, it would take approximately 300 years to reach the inner boundary of the Oort cloud and roughly 30,000 years to cross through it. No reasonable extrapolation of near-term propulsion technology gets a spacecraft to Oort cloud distances within a human lifetime. The Breakthrough Starshot initiative, announced in 2016 and funded by technology entrepreneur Yuri Milner, proposed a different approach. Ultralight laser-sail spacecraft, sometimes called starships, that would be accelerated to a significant fraction of the speed of light by an array of ground-based lasers. The target was Proxima Centauri, but the same technology applied at lower energies could reach Oort cloud distances in timescales of years rather than millennia. A craft traveling at even 1% of the speed of light, roughly 3,000 kilometers per second, would reach 2,000 AUs in under 3 years. At 10% of the speed of light, it would cross the full extent of the Oort cloud in decades. The technology required is not available today, and the engineering challenges are enormous. The laser array needed to accelerate a star chip to a significant fraction of light speed would require gigawatts of sustained power output and precise atmospheric compensation. The spacecraft would need to survive the acceleration phase, operating conditions in deep space, and the communication challenge of transmitting data across hundreds or thousands of AU with minimal transmission power. These are genuinely hard problems, but they are engineering problems, not physics problems. Nothing in the laws of physics prohibits this approach. The question is whether the civilization building such a system has the patience, the resources, and the institutional will to see it through across the decades it would require. What such a mission would find, even if it could not stop and merely flew through, would be transformative. Direct images of Oort cloud objects, actual photographs of material in its undisturbed state, not cometary material already heated and outgassing in the inner solar system, would give planetary scientists their first look at the chemistry of the early solar system in its most pristine form. Spectroscopic measurements of thousands of objects as a fly-through mission passed them would build a chemical inventory of the outer solar system richer than anything currently imaginable. And simply knowing that something built by human hands had crossed that threshold, had actually reached the place where the sun's direct influence ends and the galaxy's influence begins, would represent a qualitative expansion of humanity's reach into the universe. The interstellar objects provide a different kind of access to the same scientific questions. Oumuamua and Borisov both passed through the inner solar system, where instruments could study them in detail. Borisov in particular was close enough and slow enough, by interstellar object standards, to allow extensive spectroscopic observation, and the results showed a comet compositionally similar to solar system comets, suggesting that the chemistry of planetary formation produces similar results across different stellar systems. Every interstellar object that passes through is a free sample from another solar system's equivalent of the Oort cloud, arriving without any mission cost, analyzable with instruments already in place, telling us something about chemistry that formed around other stars billions of years ago. The Rubin Observatory will likely detect more of them. Its survey cadence and sensitivity should reveal interstellar objects smaller and fainter than Oumuamua or Borisov, extending the sample size from 2 to potentially dozens over its operational lifetime. Each one is a data point about the broader galactic population of planetesimal material, evidence that the processes that built our Oort cloud are universal, that other stars have their equivalents, and that the frozen material from those systems is traveling through interstellar space in both directions. Some fraction of what our Oort cloud contains may have been captured from other star systems when the Sun passed through its birth cluster billions of years ago. Some fraction of what we've ejected over our solar system's lifetime is currently drifting toward other stellar systems, carrying our chemistry outward. The Milky Way is, in this sense, a system of connected outer comet clouds, loosely interpenetrating as stars move through the galaxy, exchanging material over geological time. The void between stellar systems is not hermetically sealed. The Oort cloud is the solar system's contribution to a larger reservoir of frozen material distributed through the galaxy. And what happens at that scale, slowly, over billions of years, across the enormous distances between stars, is the chemistry of planetary formation propagating through a galaxy, star to star, cloud to cloud. This realization that our solar system's icy outer shell is part of a larger galactic system of such shells, that material exchanges between them, that the interstellar medium carries the signatures of formation events across stellar distances, represents one of the most recent and most consequential shifts in how planetary scientists think about the Oort cloud. It stopped being just our problem, or our feature, or our structure, sometime in the last 2 decades of research. It became a node in a galactic network, and that reframe changes everything about how to think about its significance. The Sun itself is embedded in this network, traveling its 225 to 230 million-year orbit around the galactic center. It moves through regions of varying stellar density, varying interstellar medium density, and varying encounter rates with other stars and giant molecular clouds. Each passage through the galactic plane, which the Sun oscillates through roughly every 30 million years, as it bobs up and down while orbiting the center, brings it through a denser region where gravitational perturbations on the Oort cloud are more frequent and more intense. These episodes of increased perturbation may correspond to episodes of elevated cometary flux into the inner solar system. Elevated cometary flux, in turn, means elevated impact rates. And elevated impact rates, over geological time, can produce the kind of mass extinction events that the fossil record documents occurring on semi-regular intervals over the last several 100 million years. The connection is speculative and contested. The geological record is noisy enough that establishing a precise periodicity to extinction events is genuinely difficult, but the mechanism is real. The galactic orbit of the Sun is not separate from the history of life on Earth. Every time the solar system crosses the galactic plane, the Oort cloud experiences an episode of increased stirring, and the inner solar system experiences the downstream consequences. The history of life on Earth and the galactic dynamics of the Milky Way are the same story told at different scales, connected through the mediating structure of the Oort cloud. None of the people who lived through any of the major extinction events in Earth's history understood what was happening or why. The end Permian extinction, 252 million years ago, the largest in Earth's history, eliminating roughly 90 to 96% of all marine species and 70% of terrestrial vertebrate species, left no witnesses capable of connecting what they experienced to galactic orbital dynamics and an outer comet cloud they couldn't see. The end Cretaceous extinction, 66 million years ago, killed the non-avian dinosaurs and gave mammals the ecological space to diversify into the enormous variety of forms that eventually produced us. Nobody alive at that time, nothing alive at that time, because no mind complex enough to witness it as a process existed yet, understood what was happening. We understand it now. Not completely, not with full confidence in every detail, but in broad outline: the galactic orbit of the Sun, the structure and dynamics of the Oort cloud, the mechanism by which galactic perturbations translate into elevated cometary flux, and the way that elevated cometary flux affects the inner solar system and the biosphere it contains. 4 billion years of planetary evolution, 500 million years of complex animal life, 252 million years since the worst mass extinction in history, and perhaps 300,000 years of anatomically modern humans. And in this tiny sliver of time at the end of that sequence, a particular species on a particular planet in the outer Orion arm of the Milky Way developed the mathematical and observational tools to understand the connection between galactic dynamics and the history of life on the planet it inhabits. That's not a small thing. That's one of the more extraordinary facts about the current moment in the history of this solar system, that something living inside it has, for the first time in its 4.6 billion year history, figured out what it actually is and how it actually works. The Oort cloud is the part of that story that sits at the boundary between the solar system and the galaxy, the place where what is ours and what is the Milky Way's blur together, where the Sun's gravity fades to the point where galactic tides take over, where the comets that built our oceans and possibly seeded the chemistry of life have waited for billions of years in frozen darkness before falling inward to participate in the inner solar system's ongoing story. Understanding the Oort cloud fully means understanding that you are embedded in a structure that connects you to the galaxy, not metaphorically, physically. The outer reaches of the place you call home extend far enough into interstellar space that the nearest other stellar system's outer reaches may be reaching back. The frozen material orbiting the Sun at 100,000 AU is following orbits shaped not just by the Sun's gravity, but by the collective gravitational pull of billions of other stars in the galaxy. The comets that will fall inward over the next million years are being set loose right now by forces operating at galactic scales. And you are here, at the center of all of this, on a rocky planet orbiting a modest star, thinking thoughts no object in this solar system has thought before, understanding things no mind in this solar system has understood before, reading the return address on messages that have been in transit for tens of thousands of years, sent from a place so far that light needs nearly 2 years to cross it. The Oort cloud, 2 trillion objects, nearly 2 light-years across, 4.6 billion years old. Every long-period comet that has ever blazed across Earth's sky, a delivery from this place. Every culture that has ever looked up and felt something at the sight of a comet was responding, without knowing it, to to a messenger from the frozen edge of everything familiar. Consider for a moment what it means that all of this was worked out from the ground. Jan Oort, in 1950, sat with a dataset of cometary orbital parameters, angles and velocities measured by observers at terrestrial telescopes, and extracted from those numbers the existence of a structure so remote that no instrument of his era could detect it directly. No spacecraft had yet left Earth. The space age wouldn't begin until 1957. The tools available were a mathematical framework, accumulated observational data, and a clear enough mind to see what the data implied. From those ingredients, he built an accurate picture of the outer solar system that has held up through 7 decades of subsequent observation and refinement. Oort reached a similar conclusion 18 years earlier, with similar indirect methods, suggesting that the evidence pointing toward the Oort cloud was strong enough that multiple independent investigators, working in different countries with slightly different datasets, converged on the same structure independently. The Oort cloud announced itself through its messengers, and the astronomers read the announcement correctly. Now you know what it is. And knowing that, I think, makes the universe a little more real, a little more present, and a little less empty than it looked before. Drop a comment if any of this cracked something open for you. Which moment was it? The scale, the Voyager numbers, the idea that the outer clouds might be touching right now, the fact that Jan Oort worked it all out in 1950 from cometary orbit data alone. Whatever it was, I want to know who's out there and what's landing. Until next time.